Hey folks, it's David with Streaming Relativity, home of the Astro DNA Observatory, and this is part 3 of a tutorial series that I'm doing on astrophotography mosaics. And we're going to cover how to process a 9-panel astrophotography mosaic using Pixinsight. If you've not seen part 1 or part 2 of this tutorial series, I recommend you do that, and I'm going to leave links in the description below. And in part 1, I cover the planning process, how I go about planning mosaics, and in particular this 9-panel mosaic that we shot in Gemini. And in part 2, I cover data capture using Nina, as well as some simple composition using the Microsoft ICE utility. And you'll see, I did a video which shows the results of that very simple composition, and I think the results are awesome. But we can do a lot better. And if we spend just a little time in Pixinsight, we can take care of some of these, well, let's just call them imperfections, specifically around the edges where these panels stitch together. And I call these stitching artifacts, and we're going to address how I correct for those in Pixinsight and how we avoid them in the first place. So the workflow will involve 8 steps in Pixinsight, and if you follow these steps, you have a really good chance of assembling a really nicely aligned multi-channel mosaic. And let me start by saying this is not necessarily rocket science. In fact, there are many videos out there that do discuss the workflow that I'm going to share today, but very few of those videos discuss this process and demonstrate it with a large number of panels. You'll see it often with 2 panels or 4 panels. And trust me when I say, when you get to higher dimensions, when you get to 9 panels, the devil's in the details. And so you're going to run into issues that you might not necessarily see with 2 panels or 4 panels. So especially when you're working across multiple channels. In our case, we're going to be working with luminance data, hydrogen alpha data, sulfur data, O3 data, and 9 panels of each. So this can be a bit of a chore, and you have to be patient. And I'll go through all the steps one by one, and I'll show you exactly how I get to the outcomes that I get to. Okay, there are 8 simple steps in our linear workflow for mosaics. And these steps ultimately lead to what I'm calling master mosaics for each of the channels, those being luminance, HA, sulfur, and O3. Okay, step 1, we're going to organize our workspace and our file system. Step 2, we're going to register and align the individual panels across the channels. Step 3, we're going to perform a dynamic crop on the panels across the channels. Step 4, we're going to perform our typical linear processes of background extraction and any other things that you like to do in advance of your image processing. Step 5 is that we're going to plate solve these panels and reinsert the world coordinate system data. That allows for step 6, which is to use the MosaicsByCoordinates process to register these panels in the context of the final mosaic. Step 7, we're going to perform a dnaLinearFit, which is simply a process to match the intensities of panels within the same channel. And then the final step, step 8, is to take those panels and to stitch them together using the GradientMergeMosaic process. Before we jump in, if you are into astronomy and all things astrophotography, go ahead and subscribe. I really would appreciate it. And for those that have, thank you so much. And I really appreciate the likes and the comments. I think we've got a great channel here, really good community developing, and I would certainly appreciate your support. All right, let's jump into the tutorial. Okay, let's get organized. And we're going to start by creating a linear workflow folder under a processing directory for the target that we're imaging. In this case, it's the mosaic of the IC443 supernova remnant. That's why I decided to name this image. At any rate, within that linear workflow area, this is where we'll save our main Pixinsight project. You can see this is a very large project. It's around 77 gig in size. But you'll also notice that I have subfolders, one for ultimately the folder that will house the mosaics for each channel that we're creating, and then a subfolder for each of the channels. We do this because in this workflow, we're going to be creating a number of intermediate files that need to be stored on disk. And when you're dealing with 9 panels, there are a lot of files here. So keeping them organized by channel, I highly recommend. Now, opening up the project takes about 5 or 10 minutes at this point, so I have it open on the screen already for you. And what I'll point out is that I name my workspaces. And you can create as many workspaces as you need, but I have created workspaces so that I can isolate the workflow that's associated with each channel. So my luminance, my sulfur, hydrogen alpha, my O3. But I also have a workspace that I've named alignment, where I focus on things that the entire mosaic across all channels. So there are certain operations that we're going to take that cross channels. So having a workspace where we can keep the files for each channel is important. So that is what we have here, the alignment. And in fact, that is what we're showing. So let's talk about alignment, because that's the next step. Once we have our project workspace set up, what you're going to do is pull in all of the stacks for each of the channels that you have shot, if you're shooting multi-channel. So I have here, and I've labeled these for convenience, panel 1 through panel 9, _ the filter. So my luminance, my sulfur, my hydrogen, and my O3. And what I'll point out is that these are the stacks that I created with Cyril, and that's covered in a different video. But if we were to open up each of these individual panels, we're going to see that they don't necessarily align. These images don't actually align at this stage with each other. So panel 1 across all of the channels, it just doesn't align. So the very first step that you're going to take is, for each panel, you're going to register and align each of the channels. So I've actually have a setup processes for each panel on the right here. So aligning of panel 1. I chose a reference image of the luminance channel, and then I've added the panel 1 of sulfur, hydrogen, and oxygen. And when you run this, it will align these panels so that they are registered against the luminance channel. You do that for each and every one of the panels. So there's a process here for each and every one of the panels. After this step is complete, you now have all of your panels registered against the luminance channel. You can choose whichever channel you prefer. I chose luminance. And then we can move to the next step, which for me is a crop. You know, look, the edges of your field of view with any camera are going to be the ones that are affected by your optics. So in my case, I happen to have a back focus nailed on this rig, but I am using a APS-C sensor with 2-inch filters, and I have experienced at times a little vignetting around the edges. But that can be addressed, believe it or not, with background extraction and other techniques. But what I like to do is make sure that we have clean signal all the way around the frame. And what I do, since I have a 20% overlap in the capture routine, what I do is I actually apply a global crop against all of the registered panels of 3%. So I take 3%. So I know what the pixel, my dimensions are, X and Y dimensions of my sensor. Well, and I know I have a 20% overlap planned into the mosaic. Removing 3%, finding the center, and then removing and creating a width and height equal to 97% of the sensor array will essentially give you a 3% crop around all the images. You will find that some of these panels, even with a 3% dynamic crop, might have missing signal at the edges. So what I then do is I go through each and every one of my panels, and I open the panel and I take a look to see, is there any missing signal on the edges of my frame. And in this case, it turns out that I was still missing on panel 4 and panel 7. I still had some signal missing at the edges. Once you know that you still are missing signal, you need additional cropping. The signal is missing on the top or bottom of the frame, then I will apply the crop to the entire row. So if it was row, let's say it was panel 7 is going to be row 3 of our mosaic. So every panel in row 3, I apply a crop. So I had to apply a small crop to panel 4 and panel 7, which happened to have been row crops. So I had to do some additional cropping on row 2 and 3. So 6 of the 9 panels went through secondary crops. And at that point, I now have perfectly aligned panels, perfectly cropped, and I can begin my linear processing. And I keep it very simple. I do an automatic background extraction on the cropped aligned panels. So here's an example. This is panel 4 in HA with background extraction applied. That is the _ABE extension. Okay, so now we have all of our channels aligned, cropped to the exact same dimensions, and background extraction has been applied. So in Hydrogen Alpha, I've moved copies of the background extracted, cropped, aligned panels, and I rename them to HA, the filter, _P1 for panel, for example. So this is our panel 1 in HA. Okay. In addition to that, I go out and I save each of these files to a local drive, save as, and I put it into the folder, the channel folder, HA, but then I save it as HAP1, and I save it as an EXIF file, which is a format that is that Pixinsight promotes as opposed to FITS. And I think that there are processes and scripts that are written in Pixinsight that are specifically for the EXIF format. So might as well save it out as an EXIF. And once we do that, we can go ahead and plate solve each of these. In Pixinsight, there's image analysis under scripts, and then there's an image solver. Okay. Now, if we would open up image solver, there's a couple of things you should know about this. You can add all of the files. For example, we could add all the HA files. Let me just I'll remove all these files. I'll clear this file list. So we can go ahead and add, if we wanted to, our HA panel 1 through panel 9, etc. I will demonstrate this. Now, we can add these, our 9 panels, to a list of files that we want to plate solve for. And we can even go ahead and search for an object, IC443, supernova remnant, jellyfish nebula. We can select it, say OK. And we can set the date and time of the actual observation, roughly is fine. Let's say it was on the 8th at, we'll go with 12 o'clock midnight. And you can go ahead and tell it, and you can use the automatic catalog. If you have a local XPSD server, you can do that. But for simplicity, we can go ahead with ICRS. Now, if I say OK here, and I'm not going to, this will go out and begin plate solving each of these images, and it will generate an instance of a new file on disk with a suffix of _WCS. WCS stands for World Coordinate System. Now remember, the stacks that we took in, and as soon as we aligned them and cropped them and started working with them, they became essentially pixel arrays. And they no longer have a reference system. They no longer have their right ascension or declination data associated with them. This reestablishes that information through a plate solve action. Now, I'll point out that when working with lists of files, I have run into problems where it is unable to solve all of the files. It may throw an exception on a couple of them, and then I have to go back and solve those individually. So I'm not sure whether or not that is a bug, but you can give it a shot, and if it works, great. If it does not work, if it fails to plate solve one or more of the images, then you can go in and individually plate solve those. Now we have our files that we need for another script, which is underneath Mosaic, which is called MosaicsByCoordinates. Okay, so MosaicsByCoordinates, I'll clear this list and we'll add files. In this case, we will take these plate solved files and we will add them to our MosaicsByCoordinates dialog. Okay, so at this point we should have all of our files, 9 of them, and at this point this is plate solved information. It will determine the best projection algorithm and know how to calculate the center of the mosaic. All of this will be done automatically. And the output, you should choose where you want the output to go. And I was working with O3, but you can choose your output to be in the HA directory. And now this will wind up creating another set of files with an underscore registered, and you see them here. I've dragged them into the workspace after they're created. So I won't. The reason why I'm not hitting OK on these things is that it actually takes a long time to execute these. The more panels you have, the more time it takes, and I don't want to waste the time on the video. Just follow the process that I'm describing, and you'll be OK. So at that point, you now have your registered. And what does this look like? So if we open up and we were to take a look at a couple of these, so we have 1 and 2 open. So now if I place 1 or 2 together, overlapping, and I press, you'll notice that they are aligned and they're beginning to form our mosaic. So if I go ahead and do this, you'll notice that panels 1, 2, and 3 are now registered with each other, but in the context of the final mosaic. So we have a lot of black space here, right? And so now we see how each panel will line up. And again, you're going to do this for each channel. And remember, we took the time in advance to make sure that each panel across each channel is also already registered and aligned to each other and cropped the same way. So the mosaics that we're building right now on each channel are going to actually overlap really nicely. They'll be aligned. Now we get to this next step, a linear. We're going to do a fit, but we're going to use a utility that is called the dnaLinearFit, and this is a script utility that you have to download. Okay, you can download and get more information on this script from the author's website. Now, the author's name is David Alt. I believe this script was first developed in around 2015 or so. I'm not quite sure how often it has been updated since then, but the website is called trappedphotons.com, and you'll see that he has a post on Pixinsight Mosaics where he actually does a discussion of how he processes mosaics in Pixinsight. It's actually a very good article. He used slightly different techniques for the registration of the panels, but in the end, he does talk about his utility, which he talks underneath a section called intensity matching, and there is a link with a download, a here link to download his utility. So why do we do this dnaLinearFit step? What is this all about? Well, this is to match the brightness levels of the panels in your mosaic, and this is done across all the panels of a given channel. So all the panels in your hydrogen alpha, for example, all the panels in your S2 or O3 or your luminance. There are going to be variations in the background brightness for each of these panels. And so we want to normalize that brightness and reduce these variations and achieve a certain consistency in the background intensity levels for all the panels in a given channel. Now, the key here is to perform this specialized linear fit in an order that's driven by the geometry of your mosaic. Okay, if you're dealing with a two-panel mosaic, it's pretty straightforward. You're going to normalize one against the other. But what happens when you go to a nine-panel mosaic like ours? Well, in that case, we have panel 5 at the center of our mosaic, and what we could use a dnaLinearFit to do is reference 5 as our intensity level, and then fit or target panels 2, 4, 6, and 8 using 5 as a reference, and that will give us essentially 5 panels that are now normalized. And then we can proceed to the next step, and we can reference 2 and then fit target 1 and 3 panels to be normalized against 2, where 2 has already been fit against 5, and then we can of course go and reference 8 and target panel 7 and 9, and essentially pull all the intensities to a level that is set by 5. Okay, so here we are back in the Hydrogen Alpha workspace, and I'll point out that we've created our registered panels. What I do is I immediately duplicate these files, and I rename them and save them as _fit with the _fit suffix. So HA panel 1 _fit through HA panel 9 _fit. And remember, you're going to do this for each of the channels that you'll be composing your mosaic from. And so by saving these out to file, the reason why I do this is I want to preserve the original intensities of the registered panels, and that way I can compare what the result of the fit is. Now, as I mentioned, we would start by referencing panel 5, and I'll show you how this utility works. So basically it's underneath scripts. If you install it according to the instructions, utilities, and then you'll find dnaLinearFit. Now, linear fit, you choose a reference view, as I mentioned, and you work a pair of panels at a time. So if we wanted 5, if we wanted to fit panel 4 against panel 5, we would choose panel 4 as our target. And the linear fit method, I looked at the code. There are several different ways that this linear fit algorithm will work on the overlapping regions. And if you can always open up the script and look at the JavaScript behind this, but I'm using the mean median as the approach. And so with this, when you execute, it will replace the target view with the fit version of the panel. So this is how you go about doing it. So it's a little tedious. You have to do it for each of the adjacent panels and work your way in the order based on the geometry of your mosaic. Okay, we are now ready for the finale, which is step 8. And what we need to do is merge these linear fit panels into final mosaics, one for each channel. And I like to call those channel masters. So we'll use the GradientMergeMosaic process, which is found under the domain gradient menu. And GradientMergeMosaic will gracefully merge the overlapping signals of these panels to create one seamless mosaic. And everyone lives happily ever afterwards. No, it's not exactly how it works. The merging of these panels is performed using some domain gradient calculus, which requires the right parameterization to generate effective results. And so let's make sure we understand what the process needs and how it can be tuned, and then we can move forward. So we'll go forward with some examples in this mosaic. So it starts with the files. Obviously, the GradientMergeMosaic process will work on all the fit panels from our last step. Now, the order of these files will or will not matter depending on the combination method that you specify using the type of combination drop-down box. Okay, so there are two methods of combination, and one is the average method, where the order of the files does not matter. The final merge signal will be based on some average of those overlapping regions. In the overlay method, on the other hand, order does matter, and panels in the list are going to be stacked on top of each other in the order that they appear. So the first file on the list is on the bottom, second sits on top of that, etc., all the way down the line. And the merge signal will be based on the topmost overlapping of the overlapping panels. Okay, so if we move on over to the Luminance workspace, you'll notice the GradientMergeMosaic utility up with the 9 panels loaded in a particular order. You're going to find that you're going to experiment with both combination methods, average and overlay. So when I load these files into the list, I actually load them in the order, assuming overlay. So you'll notice that 1, 3, 7, and 9, and these happen to be the corner panels, are essentially on the bottom of my image. And then I overlay the sides 2, 4, 6, and 8, and then finally the 5th panel, the center panel. That's just in case I choose to use the overlay method. So when we run the average method on the Luminance panel, and I actually ran the default values, you'll see that it's not a very pretty outcome. In fact, there's I very clearly see that there are multiple panels here. There's alignment issues. There's a bunch of things that just went horribly wrong, it seems, here. Now, interestingly, each of these artifacts happens for different reasons. And so what we start to do is adjust what parameters are available to us. And one of the things that we can adjust is the shrink radius. And we would do that if we see seams that are kind of disrupted from panel to panel, and we want to increase essentially the micro cropping around those panels, eliminating edge pixels and hopefully getting better data to merge on. I find that this actually isn't really impactful for this data set, not nearly as much as the feather radius. In fact, the feather radius is where you have scenarios where you want the signal to be merged over a wider band of pixels. By default, it comes in at 10, but I actually found that increasing that steadily and iteratively, I started to eliminate more and more of these pinched stars and these blurry sections here. And in fact, let's take a look. Running the average fit with, I believe this was with a feathering of 150, we still have some issues here. We had some remaining issues in here with alignment. And but we started to get better gradient from panel to panel. Still not good enough. So I believe that I immediately shifted over to overlay methodology. And in this case, this was overlay using the default values again. And I felt that I knew I was going to have artifacts, but I felt that the overlay method, other than this one panel area here, showed more promise with the default values. So I continued to experiment with overlay, increase and add some feathering. So now the feathering has already eliminated a number of the artifacts. We still have this very interesting intensity seam, which for me is very obvious. So let's increase the feathering even further to 100. And now with 100, we see no more, still see a little bit of rotational issue here that eventually I take care of by increasing the shrink radius just a notch. I think I go to 2. And then I'm just left with an artifact here, little bit of artifact there. So my final shot at this was by increasing the shrink radius and feathering to 150, and this was a more acceptable merged mosaic master for the luminance channel. Now when I ran this against my narrowband channels, let's go to hydrogen alpha, I actually found that I would go, and I started with the average at a feathering of 150, and I was actually very satisfied with that result out of the gate. And in fact, this carried over into each of the narrowband channels using an average with a feathering of 150 and the standard shrink size of 1. Gave some pretty good results. Okay, the final step is complete, and really at this point this is about transitioning your files to the nonlinear workspace. Very straightforward. I saved out the linear files, including the gradient merge mosaic settings that I used to create them, and then I pulled them into a new Pixinsight workspace and did a stretch on each of them. And I actually saved those out as well, stretched master mosaics. So I have these for future processing. Not a lot of data in this, so we can't expect much. But I did eventually do a very, very quick stretch on this, and no, of course we don't have enough data, but this is just to show you that it actually does concentrate on seams and artifacts, and you'll note that there are none. It's actually not terrible. Don't worry about the color imbalances. Don't worry about the stars and all those good things. When I get about 5 hours of data on each channel, and I'm going to throw in some broadband as well, this is actually going to turn out to be a beautiful mosaic. And the good news is that everything that we've done today in Pixinsight in this tutorial is can be reapplied to new stacks as I create them with more data. All right, with that, we now know the 8 simple steps to assemble mosaics, large multi-panel, multi-channel mosaics with Pixinsight. All right, folks, that's a wrap, not just on this video, but on the 3-part series for mosaics. I promise I'll revisit this particular image in the future once I have all the data and I do some broadband processing. I really am liking this image, and I think over time it's going to turn out to be a beautiful one, maybe even one for a poster. At any rate, listen, if you like astronomy, and if you like astrophotography, all things astrophotography, then please go ahead and subscribe. I think you'll enjoy the channel. I think you'll like the people that are forming the community here. So with that, I will see everybody on the next video.